Electricity powers our lives, from lighting up homes to running high-tech machines. But how does it all work? Today, let's break down the buzzing world of current electricity, from fuses to Franklin's kite, and everything in between, fast, clear, and shockingly simple. A fuse is a safety superhero in electrical circuits. It's a protective device that stops overcurrent from frying your appliances. It's made from an alloy of lead and tin, chosen for its low melting point and high resistance, but only compared to the usual wiring. When the current gets too high, boom, the fuse melts and breaks the circuit. It's always placed in the live wire to cut off power instantly and prevent overloading. Earthing is another life-saving setup. It connects appliances to the ground to prevent shocks. And about resistance? The fuse wire has more resistance than the usual copper wire, but less than the load. That's the balance that makes it work. In a series circuit, the same current flows through all resistors, but the voltage drop differs. One bulb fails, all go out. In a parallel circuit, the voltage remains the same across each branch, but the current splits. One bulb fails, others keep shining. Electric current is the rate of flow of electric charge. Think electrons on the move, from positive to negative terminal in a circuit. The concept? Discovered and defined through centuries of study. When current flows, it creates a magnetic field, a phenomenon called the magnetic effect of electricity. It's strongest at the center of a current-carrying loop, where magnetic field lines are packed tightly. Move away from the center, and the field fades. Biot-Savart's law tells us how strong that magnetic field is, based on current, distance, and the shape of the conductor. Fleming's left-hand rule. Use it when a current-carrying wire is placed in a magnetic field. It predicts the direction of motion. Fleming's right-hand rule. Flip it. This one helps us find the direction of induced current in generators. Left equals sign motors, right equals sign generators. In 1752, Benjamin Franklin flew a kite during a thunderstorm. Bold move. With a metal key tied to the string, he showed that lightning is electricity. When the key sparked, he proved a shocking truth. Lightning and static electric sparks are the same thing. Static electricity happens when charges transfer from one surface to another. Rub a balloon on your head and boom, your hair stands. One object loses electrons and becomes positive. The other gains electrons and goes negative. Some liquids, like salt water, vinegar, lime juice, conduct electricity because they split into ions. But distilled water? Not so much. It's a poor conductor with no free ions. When current passes through conducting liquids, chemical reactions happen. These are called the chemical effects of current. EMF, or electromotive force, is the total energy supplied by a battery per unit charge. Voltage, or potential difference, is the energy used by components in the circuit. So, EMF equals sign supply, voltage equals sign usage. Subtle, but important. Why use copper wires? Because they're superconductive, have low resistivity, and resist corrosion. That means they're perfect for safe, long-term wiring, but remember, longer wires equal sign more resistance. From fuses to Franklin, loops to liquids, now you know what really flows behind your switches and sockets. Stay curious, stay safe, and remember, electricity is powerful, but understanding it is empowering. Like, share and subscribe for more smart science in minutes.